Hello, 8th grade students, and welcome to lesson 3.2. We're going to talk today about rate of change and slope. So in our previous lesson, we talked about proportional relationships, and we remembered how to find slope, and we remembered that slope, got to get the right writing tool there, and we remembered, that was an eraser, so let's go here. And we remember that slope is the letter M stands for slope, and it's y2 minus y1 over x2 minus x1. So we're comparing 2 points on the coordinate plane. So another way to remember this was the change in y over the change in x. And then we also spoke a little bit about it being rise over run. So there are lots of ways to think of slope, and that's what we did last time when we were talking about proportions. So today we're going to talk specifically about rates of change, and the definition of a rate of change is it is the ratio of the amount of change in the dependent variable compared to the amount of change in the dependent variable. So remember the other day we talked about what comes first goes in the numerator and what comes second goes in the denominator. So the rate of change is going to be the dependent variable over the independent variable. All right, so if it gets confusing, think of this alphabetically. So D comes before I, so D goes first, then independent. So if you can't remember it, just think of some sort of tricky way that will help you remember it. The other thing we need to talk about a little bit is we need to define dependent and independent, all right? A lot of times we get this confused, so I want to talk to you about what is dependent compared to what is independent. So someone or something that is dependent depends on something else to function. So you, as 8th grade students, are dependents. You depend on your parents for housing, for food, for clothing. Living out on your own would be very difficult, even though I know a lot of you think that you could. You are dependent on your parents. And then your parents are independent. They earn their own money. They pay their own way. That is independent. So a child depends on their parent. The parent is the independent. Another example would be, your wage. When you go to work, the amount you earn, so your earnings depends, if you're working at an hourly job, your earnings depend on the number of hours you work, all right? So the more hours you work, the higher your earnings will be. So that's an example of dependent and independent variables. Let's look at a couple other examples. In number 1, I am on page 79 of your textbook. Eve keeps a record of the number of lawns she has mowed and the money she has earned. Tell whether the rates of change are constant or variable. So she's got a record, and she put it in a table form, and she's got the number of lawns, the amount she earned. She's got each day broken up. So on day 1, she mowed 1 yard or lawn, and she earned $15. On day 2, she mowed 3 lawns, and she earned $45. On day 3, she mowed 6 lawns, and she earned $90. And on day 4, she mowed 8 lawns and earned $120. So the first thing we're going to do is identify the independent and the dependent variables. Well, is the number of lawns she is mowing dependent on the amount of money she is earning? Or is the amount of money she earns dependent on the number of lawns she mows? So in this case, the amount of money she is earning is dependent. Let's see, I don't want to use that. I want to use the amount of money she earns is dependent on the number of lawns she's mowing. Okay, the money depends on the lawns. If she mows one, she gets $15. So the money goes on top in the numerator, and the number of lawns is independent, so it goes in the denominator. So we identified that independent is the number of lawns. She can mow 0 lawns or she can mow 10 lawns. And that is going to be the independent variable. And the money she earns is dependent on the number of lawns. Next, you're going to find the rates of change. So we're going to start comparing. And they're going to compare day 1 to day 2, but we're really looking at it backwards. We're going to look at it this way. Okay, so we're taking, this is day 2, and we're subtracting day 1. Okay, I'll put day here. Day 2, day 1. And remember, you got to go in the same order for the numerator and the denominator. So day 2 had $45, and we put dollars in the numerator, and we mowed 3 lawns. So we put 3 first in the denominator. So you have to keep everything in order. And we're subtracting that from the day 1 statistics, which is $15 and 1 lawn. And when we subtract, we get 30 over 2, and that divides to $15 or 15. And then we do the same thing from day 3 and day 2. So we'll take 90 with 6 lawns minus $45 and 3 lawns, and we get 45 over 3, which reduces to 15. We're going to do the same thing with day 4 and day 3. We get 120 minus 90 over 60, and we get 30 over 2, which reduces to 15. So they ask us, is the rate of change constant or a variable? It is constant. Every time it was the same rate of change, which is 15. So it is a constant rate of change. So it's as simple as that. So let's look at number 1 under your turn. It says the table shows the approximate height of a football after it is kicked. Tell whether the rates of change are constant or variable. Well, the first thing we need to do, like step 1 up here, is identify the independent and the dependent variable. Again, the rate of change is going to be the dependent. And again, I can't see it from what I wrote on top, so I'm writing it again down here. The more times you write it, the better you're going to remember it. So don't think it's going to be a waste to just keep repeating that. Dependent over independent. So is the time dependent on the height, or is the height dependent on the time? So in this case, the height is going to be dependent on the time. So the higher it goes, the longer it's going to be in the air. So we're going to say the height is the dependent, and the time is going to be the independent. All right? The longer it's in the air, the higher it goes. So we're going to start putting these, and we're going to do the same thing, day 1 to day 2, day 3 to day 2, and day 4 to day 3. So we're going to start with day 2 and day 1, or it's not day, I guess, in here. It's the second statistic with the first. And so we're going to do the same thing. We're going to do 18 minus 0 over 0.5 minus 0. Okay, that's going to, when we subtract, we're going to get 18 divided by 5/10, and that is going to give you 36. The next one is going to be 31 and 18, so we'll do it over here. We've got 31 minus 18, and we have to keep them in the same order. So we're going to have 1.5 minus 0.5. And you are going to get, let's see, 30 minus 18 is 12. So that's going to be 13 over 1.5 over 1. And that's going to reduce to 13. So let me box in our answers here. And then the last one we're going to do is the last statistic and the second to last statistic, which is in the height is 26 minus 31. And 2 minus 1.5. 2 minus 1.5. And 26 minus 31 is a negative 5. And 2 minus 1.5 is 5/10. That is going to give you a negative 10. Okay, and here's that last one. So they wanted us to find the rates of change. We did. The first one was 36. The second one was 13, and the last one was negative 10. And then they want us to answer, are they constant or variable? Well, they're not constant because each one changes, right? So they are variable. And I want to look at this math talk question. It says, would you expect the rates of change of a car's speed through a drive-through through a city to be constant or variable? Okay, so a car is driving through town or through a city. Maybe it's a big city or maybe it's just through our small towns. Is it going to be constant? Are they going to go the same rate of speed the whole way through the town? Or is it going to be variable? Are they going to go a little bit and then stop, go a little slower, go a little faster, then stop? Go a little faster, a little slower. What do you think? Is it going to be constant or variable? Well, hopefully you said variable, because through a town, you've got people walking, you've got cars turning in front of you, you have bicycles that might be riding next to you that you don't want to run off the road, so you're going to slow down. You've got stoplights, stop signs. Some roads are 25 miles per hour if you're driving in a neighborhood or by a school. Other roads might be 45 miles per hour. So it all depends on the speed limits. It depends on the traffic. It depends on the stoplights, the traffic signals, the people walking. So a car driving through a town is going to be a variable speed. And because it's not going to be the same. You can't drive 45 miles through a town. Well, I guess you could, but it would be very dangerous, and we don't want to do that. So in the hopefully real world, it's going to be variable. Okay, so let's move on to our next page. We're going to now, instead of using tables to find the rates of change, we are going to use graphs. So again, I'm going to write, move it up here a little bit. I'm going to write, it's dependent over independent. And again, you guys are on a different page too. You should probably write it again up there. Dependent over independent. Okay, spelling is not my thing. So we're going to look at these graphs. We're looking at Nathan bicycling over time. What is his rate of change? So we've got time and distance. Now, what is going to be the dependent and what is going to be the independent? Okay, is the amount of time he's riding dependent on the distance that he goes? Or is the distance he's going dependent on the amount of time he rides? Okay, so that's what you got to think of. And in this case, the longer he rides his bike, the farther he is going to go. So the distance is the dependent variable, and the time is the independent variable. All right. So A says, find the rate of change from 1 hour to 2 hours. And they gave us some information, but not all of it, so we just need to fill in the rest. So the change in distance, because distance is the dependent, over the change of time, which is the independent variable. And they have, so the 2 hour mark, so here's 2, we're going to go all the way up. This is the 2 hour mark. So the distance is 30 and the time is 2. So that's what they gave us here. So now we need the 1 hour mark. Here's 1 hour and the distance is 15. So we'll fill this in, 15. And then they gave us the time was 1. So we're going to subtract 30 minus 15 is 15. And the miles per hour, 15 miles per hour. Okay, we're going to find the rate of change from 1 hour to 4 hours. Okay, so they started with 4 and they found this is the 0.4. So they did 60 over 4 minus, so we need the 1 hour mark again. Here's the 1 hour mark, which is 15 over 1. So we'll fill that in, 15 over 1 hour. Then we're going to subtract 60 minus 15 is 45, and 4 minus 1 is 3. That reduces, 45 over 3 reduces to 15 miles per hour. Okay, so far he's pretty constant, right? Now let's look at the rate of change between 2 hours and 4 hours. So the 4 hours they already put in there, 60 over 4. So let's look at the 2 hour mark is this one. This 2 and 30. So 30 goes on top and 2 goes in the denominator. 60 minus 30 is 30. 4 minus 2 is 2. 30 divided by 2 is 15. He's writing at a pretty constant rate, isn't he? So part D says, recall that the graph of a proportional relationship is a line through the origin. Okay, so any proportional relationship that we talked about the other day is going to go through that origin. The angle in which it goes through the origin might be different, but it's always going to go through that origin. All right. Explain whether the relationship between Nathan's time and distance is a proportional relationship. Well, it's pretty much a proportional relationship. 1, it goes through the origin, and 2, between every point, it is 15 miles per hour, which means the slope does not change. So yes, it is a proportional relationship. Yes, this is proportional. And we can just say, because the graph goes through the origin. Now, I want to also talk to you about this type of situation if we didn't have a graph. So if we didn't have a graph and we had this information maybe in a table, one way we could tell if it's a proportional relationship is if Nathan rode his bike 0 hours, how far would he go? He would go 0 distance. So we can see right away that it's going to go through the origin. Okay. There are other cases where it may not go through the origin, and we'll get to that soon enough. Okay. Does a proportional relationship have to have a constant rate of change? Well, yes, it does. Otherwise, it would be a line like this. So if we went through up here and then all of a sudden we went faster and then all of a sudden we went slower, this is going to be a different rate of change, and it's not going to be proportional. Okay, so remember I said it has, in order for it to be proportional, it has to have the same slope or the same constant rate of change, and it has to go through the origin. And then does it matter what interval you use when you find the rate of change? Okay, so, the rate of change in a proportional relationship. So if it's a proportional relationship, you can use any intervals you want because the rate of change is going to be constant. So does it matter what interval you use? No. Proportional relationships will have a constant rate of change. And that means it doesn't matter which ones you look at, they will all give you the same answer. So if I can't find my mouse to go down to go back up, but instead of doing hours 1 and 2, I could have done hours 1 and 3, and I would have still gotten 15. Okay? All right, you guys ready? We're going to go on to the last page. Last page. All right. We've got, let me find my mouse, widen this a little bit. We've got calculating the slope. Remember, and the slope is m. When the rate of change of a relationship is constant, any segment of the graph has the same steepness. And that's what we were talking about in the earlier one, where we could say we could look for hours 1 and 3, or 2 and 4, or 6 and 3, or 6 and 1. You're always going to get the same rate of change. And that, when we look at that, that actually is the slope of a line. So the rate of change is the same as the slope of a line. And here is that that slope formula. And it is slope, and we always use m for slope, is the change in y2 over y or minus y1 over the change in x2 minus x1. And in earlier grades, we looked at it as the rise over the run. All right, so it's the change in y over the change in x. Okay, and again, another way to write that is the rise over the run. And this is slope, and it's m. Okay, I'm trying to figure out why I can't move my screen down. Oh, there it is. Okay, couldn't find it. All right, so let's look at example 2. And we're just going to find the slope of a line. And it says you can choose 2 points on the line. Okay, so there's 2 points. And you're going to find the change in y values, which is the rise. So you're going to find 2 points, use 1. And I always like to label the points. And they did that too. So they chose this as point 1, -3, 2, and they chose this one as point 2. So they've got P2 and P1. I usually just do this, 1, 2. That's what I do when I'm looking at graphs. Okay, so then I know I don't lose track. Some people lose track and they start mixing up the numbers. So they're going to take the y value from point 2, which is 4. Remember, our points are always written x first, then y, go alphabetically. And then they're going to take the point value or the y value from point 2 and subtract the y value from point 1, which is 2. And they'll get 2. And then they'll take the x value from point 2 which is -6, and they'll subtract the x value from 0.1, which is -3. So they're subtracting a -3. And then they will get -3. So then they know they've got 2 over -3, which is also -2 over 3. Okay? And that then is the slope. Okay, so what is slope of a line telling us, basically? All right, so there's the slope of a line you can think of in a couple of ways. When it goes from left to right up, okay, this is going to be a positive slope. It's kind of like going up the stairs, okay? So when it goes from left to right and it's going up, it's going to be a positive slope. If it's like this one, where it's going from left to right and it goes down, that's like going down the stairs and it's a negative slope. All right. We also have zero slopes. Okay. So if I have a coordinate plane like this, and I have a line, let's get a different color for my line. Let's choose green. I have a line going straight across like this. This is going to have a 0 slope. All right. If I have a line that's going like this, okay, this type of line is going to be, if I have a line going like this slope is going to be what we call undefined. Okay, so there are 4 different types of slope. We have a positive slope that goes from left to right, it goes up. We have a negative slope when it goes from left to right down. We have a 0 slope where it's flat. Okay, just think of a flat ground. There's no slope to it at all. And then we have an undefined slope when it's just going straight up and down. All right, so let's take a look at, we're going to take a look at your turn on number 4 on page 81. The graph shows the rate at which water is leaking from a tank. The slope of the line gives the leaking rate in gallons per minute. Find the slope of the line. Okay, so the time goes on and the amount of water leaving the tank is going up. Okay, so we're going to see from left as we go from left to right, this line is going up, so we know it's a positive slope. All right, that's the first thing I can tell from this line. All right, then we need to use these 2 points. So we can choose which ones are going to be point 1 and point 2. So I'm going to make this one 1, and this is going to be point 2. Okay, now I need to name the points. Okay, so point 1 is right here. That goes, it's 4, 1, 2, 3. So point 1 is 4, 3. Remember, you always do the x value first. And point 2 is 8 for x, and it goes up to 6. So it's 8, 6. All right. So remember, to find the slope, we do the change in y over, oh, stop writing. Okay, let's try that again. Oh my goodness. Okay, y2 minus y1. There's a button on my pen, and if you push it, it holds that writing tool down, and I accidentally pushed it, as you can see. Okay, so slope is the change in y2 minus y1, over the change in x, x2 minus x1, and we just need to fill these in. So I'm going to rewrite my m and my division bar. So y2, okay, remember this is y, and this is point 2, is 6, and y1 is 3. So 6 minus 3, and then x2 is 8, minus x1 is 4. Okay, so I'm going to continue. 6 minus 3 is 3. 8 minus 4 is 4. And it cannot reduce anymore, so we're done. So the rise is 3, the run is 4, and the slope is rise over run, which is 3/4. Okay, that's how you would find slope. Now, I also want to show you that it does not matter which point you label 1 and 2. So let's do this again in red, and I'm going to name this point 2 and this point 1. So if I do this again, I'm going to do it over here. M equals, remember it's y2, I'm going to use this formula, y2, and again, this is going to be my new point 2, y is 3, so I've got 3 minus y from 1, here's 1, that's 6, over x from 2, which is 4, minus x from 8, or from 2, which is 8, and I'm going to subtract. I have 3 minus 6. Subtraction is adding the opposite, so I have negative 3, and it's adding the opposite over negative 4. Okay? A negative divided by a negative is always a positive, so I have a positive 3/4. Okay? So I don't want you to feel or stress out about which one can be 0.1 and which one it will be 0.2. It doesn't matter. You're going to get the same answer if you do your math correctly. All right. Gosh, you guys, I think that's all there is to our lesson. You do have some practice problems to do, and then we will check your understanding with a couple of lessons in Canvas. So I hope you have a great day and enjoy.